Hey there, folks. I hope you had a good weekend. There's a new kind of problem here that expands on the rotational concepts that we covered from the previous chapter. In this one, we're told about a grindstone, which has a particular diameter, mass, and initial rate of rotation. And we're going to sharpen the blade of an axe by pressing it against the rim of this grindstone while it spins. The frictional interaction between these two objects will cause the grindstone to slow down, and after a small amount of time, the rotation will stop completely. It's our job to take these details and use them to figure out the coefficient of kinetic friction. Let's start by drawing a picture. Here's our grindstone. I'm going to label the point at the very center where the rotational axis is located, and call that point O. Since we have the diameter of the grindstone, by extension, we also have the radius, which is much more useful. Let's also add the initial angular velocity, omega. The general convention is that counterclockwise rotation is positive, so I'll add a symbol for that in the top right corner. Now, pressing the blade of the axe against this rotating disc can be interpreted as exerting an applied force on it, like this. The applied force can be broken down into components. A normal force component that acts perpendicular to the rim, and a frictional force component that acts tangential to the rim and points in the direction that's opposite to the rotational motion. The normal and kinetic friction forces are really all that we need in this problem, so we can throw away this original applied force vector to free up some space. The plan is to use these vector components with the rotational analog of Newton's second law, which says that the net torque on a rigid object is equal to the product of the moment of inertia and angular acceleration of the rotating object. We did a bunch of problems in the last chapter that involved moment of inertia and angular acceleration, so these quantities on the right are really nothing new. That's all very familiar. What we haven't seen yet is what's on the left, torque, which is a measure of how much a force changes an object's rotation. There's a few ways to define that quantity, but the simplest form is a product of three things: a force, F, the lever arm of that force, lowercase l, and the sine of the angle between F and L, where the lever arm of the force represents the perpendicular distance between the axis of rotation and the line that the force acts along. I'll give a visual of that using our picture in just a moment. Coming back to our net torque expression, the normal force and the kinetic friction force will each have their own torque contribution on the left-hand side, which are both relative to the point O, the center of the grindstone. Let's fill in their definitions. In the frictional torque definition, I've set the kinetic friction force to be negative, since that force opposes the rotation and slows the grindstone down. We can't go any further here until we know the values of the lever arms and the angles. So I'll shift the focus back to our picture. Let's start with the kinetic friction force. If we look at the line that the kinetic friction acts along, it's tangent to the rim. It won't ever go through the center of the grindstone, no matter how much we extend it forwards or backwards. That's really important because it means we can draw a perpendicular distance from the center of rotation to that force, like this. But here's a question. How do we know that this purple length is actually perpendicular to that green vector that represents the kinetic friction force? Well, by definition, perpendicular lines intersect at a 90-degree angle. And if we can draw a right angle between these two, like that, then it meets the requirement. So this purple length is the lever arm for the kinetic friction force. And notice, it's the same length as r. Thus, we can use the radius value in place of the lever arm variable. Very cool. Let's look at the other force next. Like before, we want to first focus on the line that the force acts along. Sometimes you'll hear this referred to as the line of action. This one will definitely go through the center of the grindstone, as you can see from this dotted blue line, which represents the line of action for our normal force. Therefore, we are unable to create a perpendicular distance like we did before because there isn't one. When the line of action goes through the rotational axis, the lever arm has a length of 0. That's all that can really be said here for the normal force. Let's collect these results and go back to where we were stuck and plug those in. The torque due to the normal force will fade away, since we have multiplication by 0 going on in there, and the angle involved is relevant. In the other term, we can simplify a couple things before moving on. The sine of 90 degrees is just 1, so we don't really need that piece anymore. Additionally, we can plug in the definition of the frictional force, which is mu sub k times n. We want to isolate the coefficient of kinetic friction, so let's divide both sides by negative nr, and then plug in the definition for the moment of inertia for a disk, 1/2 mr squared. We can slide the 2 from the 1/2 downstairs, and then cancel out a factor of r between the numerator and denominator to get the following. The only thing left now is this angular acceleration term in the numerator. Since we have the initial angular velocity and the time it takes for the grindstone to come to rest, we're free to grab this rotational kinematic equation from our tool belt. The final angular velocity goes to 0, and we can swing the initial one over to the other side and divide both sides by t. There it is. I'm going to insert this ratio for alpha into our previous equation and then clean it up a bit to make it look pretty. Now it's ready for some numbers. One thing that we can't forget to do before we move on is convert the initial angular velocity from revolutions per minute to radians per second. So I've included these two conversion factors in the numerator to account for that. With that ready, we can go ahead and plug this all into a calculator. I see a couple numbers using 3 significant figures. Let's see, this one, and this one. However, 160 and 850 only have 2. So we should probably report our answer using 2 significant figures as well, just to be safe. Therefore, our solution to the problem is a coefficient of kinetic friction of 0.48. And now we're done. Thanks for watching, guys. Have a good afternoon.